Right. So right now we're going to be looking at several different specific electrophilic aromatic substitution reactions. We're going to be going over five. And so what you want to do right now is maybe pause the video, take some time, and write out these five reactions in your notebook. All right, so we're going to be looking at these five reactions, and if you think back to the mechanism that we went over, I had said that all of these reactions proceed through the exact same mechanism in terms of how the electrophile is added to the aromatic system. Right, so the aromaticity breaks, a pair of pi electrons from the aromatic system reach out and grab the electrophile, so we're making a new carbon electrophile bond. At the same time, we're forming this positively charged rhenium intermediate. And then in the second step, there's some base in the reaction that removes a proton to re-aromatize that system. So that's going to be consistent throughout all of the electrophilic aromatic substitution reactions we study in this chapter. All right, so really the only thing that's going to be different in these reactions then is the type of the electrophile that's used, right? And then the type of base that is used whenever we draw the mechanism anyway, the type of base that's used to pull a proton. So, five reactions: halogenation, nitration, acylation, alkylation, sulfonation. We'll just go through them in order. We'll start with halogenation, right? So you can see we're replacing a carbon-hydrogen bond with a carbon-bromine bond, right? And when we're doing this, we're adding bromine and a catalyst. So it's important to note that if we were to take benzene, right? If we were to take benzene and mix benzene with bromine, molecular bromine, we would get no reaction, right? They would just sit there and look at each other and nothing would happen, right? It's not until we add in a catalyst can we get a reaction to occur, transformation to occur from benzene to bromobenzene. All right, so you can see that this is not the only reaction where we're using a catalyst, an aluminum chloride catalyst, right? So the acylation and the alkylation, what's referred to as the Friedel-Crafts acylation or Friedel-Crafts alkylation, also use a aluminum chloride catalyst. So it's going to be important to understand a little bit about how aluminum chloride functions in this reaction. Okay, so we always tout the relationship between structure and function in organic chemistry, right? So the structure of something and what it's composed of, the atoms it's composed of, is going to determine the function of that substance. So in this figure here, what I have, or what I've drawn, is aluminum chloride or aluminum trichloride. An aluminum trichloride is a Lewis acid catalyst, meaning that Lewis acid is an electron acceptor, right? And so it's something that wants electrons. And so aluminum chloride has a trigonal planar geometry. So the bond angles between the chlorines are 120-degree bond angles. Right? And all four of those atoms are in the same plane. So whenever a Lewis base adds to aluminum chloride, it's going to add either from the top face of that plane or the bottom face of that plane, right? It has to interact with that empty p orbital around aluminum. When it does add, in this case bromine, so we're going to take these electrons and show them adding to that empty p orbital. When it does add, that geometry is going to switch from being trigonal planar to a tetrahedral geometry, right? And now the chlorine carbon or chlorine aluminum chlorine bond angle is going to be about 109 degrees. Okay, So it's important to understand that geometry change just from the perspective of aluminum chloride being a Lewis acid and starting out as being trigonal planar, that empty p orbital being available to anything that can donate electrons. All right, but we want to think about the reactivity of the product that's formed. Okay, and so if in bromine, molecular bromine, this is a non-polar bond. Okay, bromine, both of these bromines share electron density in the same way because they're the same atom and have the same electronegativity. Once this bromine attaches to aluminum, now these bromines are not sharing electrons in the same way, right? This bromine had given away a pair of electrons to the aluminum. All right, so it's wants electrons back, so it's pulling on both of those bonds to get electrons back. So we can say that this bond is heavily polarized towards the bromine atom that has a positive formal charge. Okay, and so that's what makes this such an exceptional electrophile and allows it to get into a high enough energy state that it can react with benzene. And so when benzene or another aromatic compound comes along, we can use those pi electrons on benzene to reach out, react with the bromine, and then the bromine on the outside, and then break the bromine-bromine bond and give those electrons back to Br. Okay, so that's what it's looking like at a geometrical scale. Let's take a look at the mechanism in full. Okay, so halogenation. All right, we're starting with bromine and aluminum chloride. So we'll draw our bromine, put a pair of electrons, or 3 pairs of electrons around that guy, and then aluminum chloride. Right, and when those react, we're taking a pair of electrons from bromine, adding them to aluminum, and we're forming the tetrahedral electrophile. And I'm going to move things around here a little bit. Okay, now our benzene comes in. Make a bond from carbon to bromine. You can draw the hydrogen here if you want. It's not super important in this step of the mechanism. And so now we've formed the rhenium intermediate. Right, so our new carbon-bromine bond, our positive charge after the electrons left this carbon-carbon bond, and our hydrogen, and then left over we have our Cl3Al. Br. Okay, and so to rearomatize, we're going to take one of these sigma bonds, the electrons in one of those sigma bonds, most likely the chlorine-aluminum bond, right? And grab a proton, we're forming HCl in this case, and our product. So there's our product. Our HCl, and then it's important to note that we're reforming a catalyst that would be BrAlCl2. Okay, so just to go over that again, what you might want to do is pause the video, get this copied down, and then we'll go over it again really quickly once you have it written down. Okay? Okay, so if you're just rejoining, we'll quickly go over this mechanism, and then we'll continue to look at the other mechanisms, really just focusing on the formation of the electrophile. All right, so in this halogenation, right, we're taking our catalyst, which is aluminum chloride. It's a Lewis acid catalyst. The Lewis base that's going to react with it is bromine. So a pair of electrons from bromine add to aluminum. We form this tetrahedral electrophile, and so this is the electrophile in the reaction. All right, so remember I said that the only difference between these reactions mechanistically is the electrophile that's used for the addition, and then the base that's used for the elimination. Okay, and so we form the reaction electrophile. It's high enough in energy, reactive enough that benzene can react, make a bond to bromine. Okay, in doing so, we're forming our rhenium ion intermediate, and then in this case, this is our base that we're using in the reaction to remove the proton. Okay, so let's look at the other reactions. We'll go through them really quickly. We'll just really look at the formation of the electrophile. And then it will be up to you to complete the reaction with the addition and the elimination, so choosing the proper base. All right, so with nitration, we're using nitric acid and sulfuric acid. So nitric acid has the structure of a nitrogen and 3 oxygens around. Nitrogen, it has a formal positive charge, and one of the oxygens has a formal negative charge. And then sulfuric acid. That should be a familiar structure. So nitric acid, sulfuric acid is a really strong acid, so nitric acid is going to get protonated. And that forms a really good leaving group, which can get kicked out to give us what's called the nitronium ion, just NO2. Inject water. All right, so when benzene reacts, it's going to react at nitrogen. Nitrogen will stay positive, and then the oxygen will get the negative charge. Acylation. All right, Friedel-Crafts acylation. Again, we're using the aluminum chloride. All right, so at this point, pause the video and see if you can come up with a mechanism yourself before I write it out. All right, so this mechanism is going to start similarly to the halogenation mechanism we drew above. All right, so we're going to take our acid chloride. Remember, 3 pairs of electrons on chlorine, and our aluminum chloride. The acid chloride will add to the aluminum chloride. Okay, so you'll notice similarly to above, right? We added a halogen to the aluminum. The aluminum adopts a negative charge. The halogen atom adopts a positive charge. In this case, what's going to happen is that the oxygen electrons can fall down and kick out that positively charged chlorine, and we form what is called an acylium ion. All right, carbon here has linear geometry. Write this out, acyl ion. All right, and then the aluminum tetrachloride, AlCl4. Okay, and so when benzene reacts, or our aromatic compound reacts at carbon, kicks a pair of those pi electrons up to oxygen to reform carbonyl. All right, it's getting pretty busy. All right, so two more, alkylation. Okay, so again, maybe pause the video and see if you can develop a mechanism that accounts for the formation of the electrophile in alkylation, right, or formation of the alkylation product. So alkylation is going to start similarly to the others that use aluminum chloride. We'll take our alkyl chloride in this case, and the aluminum trichloride. And the chlorine and the alkyl chloride will add to the aluminum. So this is the Lewis base. This will be the Lewis acid. Gotta move things around here. All right, so just note that I kind of rearrange things, turn things around. So the chlorine that we added here, now with only two pairs of electrons, and the aluminum gets a positive charge, and the aluminum would get a negative charge, right? And so this is the interesting thing about alkylation, and one thing that we have to really pay attention to is the electrophile in alkylation is just a carbocation. Right, so the way that we would represent this is this carbon-chlorine bond would break, giving the electrons to chlorine. And we make AlCl4. And then the electrophile is a carbocation, and that is what our benzene is going to react with. Okay, that's important because the electrophile that's generated in this reaction is going to behave like all of the other electrophiles we've used so far in organic chemistry, in as much as it can rearrange. If a more stable structure can be formed through a 1-2 migration, a 1-2 rearrangement, that rearrangement will occur. All right, so we'll actually take a look in the next video at some of the limitations of alkylation. All right, the final reaction is sulfonation. Right, so notice that there are two different conditions that you could use for sulfonation. I think the one I'm going to show the mechanism for is using SO3 and H2SO4. This is what is called oleum or fuming sulfuric acid, if you've ever heard that. Concentrated sulfuric acid is the other way. Using fuming sulfuric acid or oleum, that tends to be faster. It's a much better process. So sulfonation, the mechanism is really easy. So SO3, draw 3 bonds to oxygen, and H2SO4. So sulfuric acid, all that's going to do is be the proton source to protonate SO3. And then this is the electrophile for the reaction. So benzene at this point is able to react. That's such a hot molecule that benzene's able to react and form the product. All right, so just to look over this again, right, in halogenation, the reaction electrophile is outlined here in red, and the base is outlined here in red, right? For nitration, the reaction electrophile is this species, which is called the nitronium ion. Right? In acylation, we're forming the acylium ion. Okay? In alkylation, the electrophilic species is a formal carbocation, and then here we just have protonated sulfur trioxide. So in the just to recap, right? These are the 5 reactions that we were looking at. You will be responsible for knowing the mechanisms for each of these 5 reactions. Again, the mechanisms are not really that different. The only difference is in the formation of the electrophile. It really depends on the electrophile that you're using. Otherwise, the addition and the elimination are all going to be the same. All right, so in the next video, we will look at why we would want to we would want to do those specific reactions, these 5 specific reactions, and what we can do with each of the products for these in these reactions.